Welcome back, ladies and gentlemen. We are going to continue with concentration, the single most important part of solutions. Well, I mean, to be fair, all the stuff you get to make out of solutions is pretty cool. But concentration is pretty important for chemistry, so we better take a look. Concentration, what is it? It is important for chemists to know how much solute is in a certain volume of solution. When chemists speak about the concentration, they are referring to the amount of solute per unit of solution. There are several different ways to show this. What am I saying? Okay. Here's my beaker of water. Inside of here is just water. But we're going to pretend that inside of here is wonderfully deadly poison. Probably slipped to me by one of my students who wants me out of the way so they don't have an exam. How much poison is in here, though? Mr. C's pretty big. Fat. Okay, neither. But we'll pretend. Mr. C can only take a certain amount of poison. Now we can see here, or maybe you can, that there is 150 milliliters of water in here. Well, if there's only 1 gram of poison in here, Mr. C could probably drink this and be okay. Maybe a little bit sick, but otherwise fine. But what happens if there was 10 grams of poison? 20? 30? 40? How many grams of poison can we put in here before there is a problem? We have to figure that out. There must be a way. If only we had some kind of concentration that we knew was always lethal. Then we could figure out just how to off Mr. C. I mean, save Mr. C before the student gets him. Let's take a look. First method. Measure the amount of solute that is dissolved in an amount of solvent. So how much poison is there in my glass of water? Dilute solution. Okay, here's a word, dilute. Dilute. Contains only a small amount of solute in a given amount of solvent. Okay, so concentration is a measure, so it's a number. Dilute, or being dilute, means that there's like a relative comparison, right? So if this 150 milliliters of water has only 1 gram of the poison, that's not very much, so it's a very dilute solution. But if it's got like 100 grams, well, that'd be a lot. So that'd be a very concentrated solution. There it is, concentrated solution. Representing concentration, what numbers do we use? Okay, there's a couple. Grams of solute per liter of solvent. That's what I was just talking about with the deadly poison. This one is pretty common, right? Percent weight of solute per volume of solution. We see that sometimes. It's rare, to be honest. So, right, so percent weight means that you take like the mass divided by the volume of the solution times 100. That's basically what you're saying. You're just saying like what percentage of the contents of there, right? So this was 150. So we'll do a quick calculation here. If it was 150 milliliters, and I said there was 1 gram, that's not very much, times 100, we get out our trusty calculator a percentage of 0.66% of deadly poison. It's not so bad. Mr. C's probably fine. I mean, it depends. Some poisons are pretty deadly. Some poisons, that would still be enough, but not this one. This is a not very deadly poison, because obviously the student who's trying to poison me is the kind of student who didn't, pay attention in class, because if they did, they wouldn't need to poison me. They could just write the exam normally, but, pay attention, then you can poison your teacher properly. Oh, the advice I give. Okay. What do we got now? Percent volume of solute per volume of solution. So it's the same calculation, but now we're dealing with volume instead of mass. Why would we do this? This is how we would talk about things like alcohol. Usually this is used when we're talking about like a liquid mixed with a liquid, because both of them are volumes, right? Because they're both, anyway, I've got this container, I'm just going to pour in a certain amount from my second container. I don't want to mass it, because I don't want to put on a scale. I can just, look, how much is there? I can measure it. So that we use that instead. To be honest, yeah, same thing. See, exactly the same setup. But here's the thing, guys. Most of these you're not going to use. Not in chemistry. We're not going to talk. These, meh. Here they are. You've covered them. This one is going to be alcohol. This one might be a couple types of like, I'm not even sure, something from industrial application, maybe. This one you'll see in a few places. It's basically density. This is the one we're going to use. No, not this one. I lied. Parts per million. This is for air. This is for particles in the air, parts per million. So number of particles of the solute in 1 million parts of another. So this is like, is there some sort of toxin in the air or dust or ash, right? If there's a forest fire somewhere, they'll talk about there being smoke in the air, and the smoke levels being a certain number of parts per million could be a problem. Parts per billion, it's even smaller number, right? 1 billion. Public health services just reduced the permissible lead levels in drinking water from 50 parts per billion to 15. So if you've got, right, if you took 1 billion particles, so you just like picked up a giant mountain of particles, and you like fished in there and you pulled out 15 lead, health services would be like, nope, shut this down. Too much. Lead's dangerous. What can we say? Don't drink it. So these two are useful for pollutants and poisons and other things. So in reality, if we were talking about some poison in Mr. C's cup over here, we'd probably be using parts per million, parts per billion, assuming that the, fiendish student who was trying to poison me was prepared and thinking in advance. They were very studious. But since they aren't, instead we're going to be using the most important unit that we're going to see in this unit. Could I say unit more? Molarity. Okay. Molarity has got mole in the first part of it, MOL. Molarity involves the mole because it's chemistry. It's been a while since we saw the mole in any great detail. Let's take a look what we got. Represents the number of moles of solute in 1 liter of solvent. Okay. The units are in moles per liter or moles per decameter cubed, because 1 liter is 1 decameter cubed. Don't worry about that. It's moles per liter. Nobody cares about that other part. The volume is the volume of the total solvent solution, not just the solvent. Okay, that'll be important if we mix two liquids together. But what I'm basically saying is that everything in the beaker. So right in here, we've got 150 milliliters. If there was deadly poison in here, which, given how much I'm building this up, I really hope there isn't, because that would be very unfortunate. Die on camera. If there was 150 milliliters in here, and some of it was water and some of it was poison, I wouldn't know. I'd just know it's 150 milliliters of whatever's in the beaker. So the whole solution, not just the solvent part. 1 molar solution of NaCl contains 1 mole of NaCl per 1 liter of solution. So if I had 1 liter of a 1 molar solution, I'd have 1 mole. If I had 2 liters, I'd have 2 moles. If I had half a liter, I'd have half a mole. Seems pretty straightforward so far. Yeah, there's a bunch of comparison numbers. Don't worry about it. Molarity versus concentration. The units for concentration, as said, are mole per liter. This is also known as the molar concentration, or the molarity, or the capital M. Concentration tells you how many moles of solute there are in 1 liter of solution. And now we're going to write it mathematically. Here it is. Boom. Moles divided by liters. That's it. It's just how much is there inside. I've got 10 moles in 1 liter. 10 moles per liter. That's it. There it is if I write it algebraically with symbols. We use the N for moles, just like we did within stoichiometry. A V for volume, because it's volume. And a C for concentration, because it's concentration. Really, I should have done that in another order, right? I should have said, and we use V, we use C, and then we use N for moles, because N is close to M. We talked about this last time. N is just standard in chemistry for moles. It's just how it is. All right, let's do an example here, okay? What is the concentration of 52 grams of sodium chloride dissolved in 200 milliliters of water? So this is a pretty standard type of problem that might happen, right? Like your boss comes in, you're a chemist, incredibly smart, very well paid, obviously. Boss comes in and says, I need you to make me a solution. And you go, sure thing, boss, how much do you need? And he says a number and then he just leaves. And you need to know how to make it. Now in this case, we didn't even hear the number. And we're just like, well, we got 52 grams of salt here. I guess we'll just throw it in the water and hope it's enough. Let's see how much we make. So how do we do this? Okay, well, first things first, we got to turn 52 grams of salt into moles, because this whole thing is moles per liter. So all the stuff we learned in stoichiometry about conversions are coming back again. We got to do them again. Okay, here's our conversion matrix. Have, want, gain, lose, the whole thing. We've done it before. Here we go with the setup. We're going to need our periodic table. We're going to pull it out. We're going to look up the molar mass. Remember that. 52 grams of NaCl, 1 mole divided by 58.44 grams, because chlorine is 35 and sodium is 23. It's 58 minus 35. There we go. You do that math, you're going to get 0.89 moles. So we're less than a full mole. Okay, so we don't have a mole, but we also don't have 1 liter. So what's my concentration going to be? Okay, well, here's our equation. N over V equals C. 0.8 moles divided by 0.2 liters, I converted it to liters, equals 4.45 moles per liter. Now, I don't have a liter. I've only got 200 milliliters. But what I'm saying is that I have managed to put together a concentration such that if I had a liter, I would have 4.42 moles. Okay? So it's like how strong? How strong is that solution on the shelf, right? When you make Kool-Aid or lemonade or any kind of powdered drink mix, you pour in the powdered drink, you mix it up. Is it really, really dark? Or is it pretty thin? Now, if you made it, it's probably really dark because you probably poured like a ton of the stuff in there. If your parents made it, it's probably a little thin. They probably watered it down and you were like, it doesn't taste as good. Why not? Because there's less solute. There's more solvent. It's mostly water. There isn't as much of the flavor stuff. So what we're seeing here is that we're seeing the strength of our solution. How strong is that Kool-Aid solution that the parents made? And we have it with a number value, 4.45 moles per liter. That tells you numerically how strong that solution is. Now, we don't necessarily know if 4.45 molarity is really strong or not. We just know it's a number. With some practice and some time, we'll start to get the hang of it. But I would generally say, depending on the material, but let's say ballpark it, anything over 2 molar, you probably don't want to dump on yourself. Depends on what it is. Now we get to see if this is poison. If it's fast-acting poison, I'll just drop. What is the concentration of a solution in which 0.45 grams of sodium nitrate is dissolved in 265 milliliters of water? Okay, we know how to do this. Step 1, grams to moles. Step 2, we got to find the concentration. Okay, give it a go. Don't wait for me. Yes, I know. I'm going to show you the answer in like a second, but I want you to try it. So I'm going to drag it out and drag it out and drag it out, and then I'm going to push the button, and I'm going to turn around, and there's going to be the first part where we figure out that 0.45 grams of sodium nitrate is equal to 0.0053 moles of sodium nitrate. That's not very much. It's not very much. But we're only putting it in 265 milliliters. That's not a very large amount of water. That's just slightly more than this. 265 would be about there or so. So not much more. There's the final calculation. 0.2 moles per liter. Calculation-wise, this is very easy compared to stoichiometry. Yes, we're having to remember a bunch of the different things we've done before. Yes, it's painful to do that. Oh, I got to pull up my periodic table again. I got to remember what all the different molar masses are. I got to remember how to do the conversions and all that. But it's good practice anyway. And it's not too hard to do. Next one. What will be the volume? Oh, different question. What will be the volume of a 0.5 molar solution if it contains 25 grams of calcium hydroxide? Oh, there's a lot of stuff here. Let's break this down. What is the volume? So we're looking for volume of a 0.5 molar solution. So that tells us the number of moles per liter. Okay, so we know that there's half a mole for every liter, but we don't know how much volume there is. Is there a full liter? In which case this is easy. There's a half a mole. But what happens if there's like 20 liters? Well, it could be 10 moles. but we don't know. We need to figure it out. Oh, but it tells us it's 25 grams of calcium hydroxide. Okay, so if we know that there's 25 grams, we can turn the grams into moles. And then once we know the moles and the moles per liter, we can find the volume. All right, step by step. Step 1, grams to moles. Remember, calcium hydroxide, 2 hydroxides, because calcium is 2 plus. Next step, 0.34 moles from here equals 0.5 moles per liter from the question. So now we just got to find this missing volume that will make this true. All right, it's going to take a little bit of algebra. We put all that together. Boom, there it is, 0.675 liters. More than my cup can hold. It'll be like up to there. Okay, that's it. Concentration is not that fancy. It's pretty straightforward. You kind of have seen how to do it. The calculations are pretty easy, I hope. I hope you found that to be pretty straightforward. I think I already said that. But you're going to need practice, and you're going to see there's lots of practice. So I'm going to leave it there, and I will see you guys next time.